Oh, goodness. I'm stretched. Well, I guess I'll just be narrow prof for now. I'll fix it during the quiz. Hey, 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 everybody! How's everybody feeling? Are you feeling good, fancy quiz computers? Does that imply submitting the entire lab file that was provided? Yeah, so with the assignment, or the, with the Lab 1 Dropbox, if you could just, when you're finished, submit everything, and, yeah. I think that the, it's, like, we need to keep a record of the submissions, in case we have to refer to it later, so if you would please just put that in there, that would be awesome. We should use Kahoots as the quiz format. Yeah, no. Although I guess that would be kind of cool, wouldn't it? I don't know. I've never really gotten into the Kahoots thing, you know. Yeah. Maybe I should. Maybe I'm just being an old fuddy-duddy because I'm not using Kahoots for my. I don't think that the thing about Avenue is it integrates with the gradebook, which is a lot bigger a deal than you think. Do you want us to zip the files up first? Probably preferably, but you can submit multiple files, and I don't think there are that many of them, so. Bounding box. Crop. There we go. Only the top scorer in the Kahoot gets 100%. Everybody else gets a 0. No, I wouldn't do that to you. Okay. So, I was a little bit paranoid about it, actually. That's why I didn't set the quiz to, like, visible. I don't know if available on, like, at the time specified, it actually, like, prevents you from actually writing it. So I was a little bit, like, skeptical, but I'm gonna set it. I'm gonna set it visible now. According to Avenue, if I've configured things correctly, you should have the thing open for you to actually write it at 5:35 p.m. in 4 minutes. Do you need both people to submit it on Avenue? No, only one of you needs to submit it. The first answer is not B. Thank you. Jeez. And besides, ha ha ha, the multiple choice questions are randomized. So, you know, what's B for you is C for someone else. Okay. First answer not be confirmed. Again, it randomizes the order of the multiple choice questions, so all of this A, B, it's not... no. It doesn't matter. And you are silly. Silly people. So you're telling me there is a chance that it is B. Yes, there is a 25% chance, if there are 4 answers possible, that it is B. Actually, statistically speaking. Only 10 minutes to do the quiz. Yes, correct. Except for the accommodation people, of course. If you have an accommodation, then it's been worked into your writing time on Avenue, so you don't have to do anything extra. It'll operate as normally with the extended timeout. Dropped milk on your keyboard. What? Come on. How many questions are there? Let's see. 6. There are 6 questions, but the bank of questions is like... there's like... oh, I think I came out with like 44. So it'll pick 6 questions out of the 44 that I wrote for you guys, and that'll be your quiz. And again, those are also in randomized order, so... what happens if we submit, like, 1 second later? Watch the timer. It'll save your answers as you enter them, and if you don't finish the last question in time, then it just doesn't count, I guess. Also, just so you know, the, once you, like, it doesn't let you go back through the questions. I've enabled this specifically to prevent cheating. So... be sure about your answer before you click next question. But yeah, are the questions easy? I think they're pretty easy. Are they all multiple choice? A majority, or I would say a plurality of them are multiple choice. Speedrun any grade percentage. No, don't speedrun. Can you use our notes? If you can use your notes fast enough, you get like less than 2 minutes per question, right? So if you think you can use your notes fast enough, I can't prevent you, but I don't think you'll have time to use your notes. It should be from your brain. Yeah. It should give me the 6 easiest ones. That would be pretty cool. Yeah. It's only a 1% quiz, right? No stress? Yes. Open book? Yes. How short is very short? Quite short. You'll see in, like, less than a minute. What if question 1 is really hard and you want to go back to it? It won't be. Can you verify my answers before I submit? No. Time to build a bot for it. 10 seconds. 3 seconds. Quiz start! Go, 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 go! In the meantime, I'm going to be playing Burger Time. Ah. My avenue is lagging and I can't go to the next page. Give it a moment. I'll write your name down, Ethan, and if that prevents you from finishing the quiz, I'll like give you another shot at it later on, okay? Because of technical difficulties. But so if anybody is experiencing technical difficulties, let me know. Yeah, if you reopen it on a different device, that'll probably help too. Always right when you unpause. I'm on the last question and there's still 5 minutes. Am I allowed to use my notes? Yeah, I can't stop you, so go for it. Can we have RNG tests in the metaverse next semester? Listen, if Zuckerberg wants me to port my course to the metaverse, he can damn well pay for it. That speedrun was a little too quick rest, yeah. Yeah, didn't you know that I'm like the world's preeminent Burger Time streamer? Cool. Alright, so people are finishing it like sort of 5 to 7 minute range. Okay, that's good. No, of course not. No, I don't do Twitch. I'm not twitchy. Yeah. Bah. When am I doing a Super Mario 64 16-star speedrun? When I become a computer. Because only... That's a tool-assisted speedrun, right? Yeah. Alright. Seems like people are, Hey, I got all the way to, like, the last level, so... After this level, it just keeps looping from the first one. Yeah. Well, there's still 2 minutes left in the quiz, so I'll finish the level. It's like Pac-Man, but better. Oh, shoot. Fastest 0 of my life. Yeah? Oh, come on. Don't be so negative. I'm sure you got at least one. There we go. There you go. See, it's back to the first level. Alright. Let's see. Oh, you like that one, did you? I tried to put like a couple of fun answers in, you know? Am I gonna teach you how to make a tool-assisted speedrun for Super Mario? Nope. Nope, not even remotely. Alright. So, the quiz closes in like 1 minute. So, policy kit. I thought that said piracy kit there for a second. I was like, what? Piracy kit. Am I going to show the answers? No. No, I'm not going to show the answers. You should get, like, is Burger Space Turing complete? No. No. You should get feedback on your answers, though. It'll tell you what the correct answer was, I think. When will you know your results? Should be when the quiz closes for everyone. So, I think the maximum writing time for anybody in the class is 17 minutes. So at 17 minutes, I should have done T-Rex game. Maybe I will for the next quiz. Give it time, and if by the end of class nobody has their answers, then I'll set it so that it reveals them. Don't worry about it. The intention is for you to be able to see the answers, so if that's not the case, I'll fix it. Salite. So I might as well get to our lecture today. How will the short answers be graded so quickly? Oh, yeah, there are, like, 2 questions on there that actually need a TA. I remember this now. Okay, sorry, TAs. So, like, I imagine, like, between them, the TAs probably have, you know, about 10 questions to mark, which isn't bad. I might even do it myself. A lot of the, like, fill-in-the-blank answers were, like, I pre-configured it to accept specific responses, so. There were a couple of questions on it that were, like, you know, write a short sentence type thing. That's actually going to have someone look at it. But, yeah. Mine glitched at last minute. It said the quiz said time exceeded after I submitted. Weird. Yeah. Oh, like, Aaron asked me to make the Dropbox, because I think there's, like, you're getting, like, there's one thing where you're getting marked on comments in the code, and, you know, I said, well, you should just, you know, check the comments in the lab, but, you know, it might that's a thing that can be checked afterwards, so, you know. Can we ask about certain questions here? If you wouldn't mind, Alistair, just waiting until the end of class. There are some students still writing. Oh, playlist. Yeah, yeah, okay. I'll put that on my to-do list. The problem with that is, maybe I'll post it as an unlisted playlist, because, like, the problem with YouTube is, if I make it a publicly accessible playlist of unlisted videos, although the videos aren't searchable on YouTube, you can still access the videos if you're a subscriber to the channel, regardless of, or, like, if you know how to get into the playlist, you can get to the, like, it violates the privacy concern, so, and I was having some issues with some trolls at the beginning of the semester, so I clamped down on the playlists, but I'll put that back. Playlists. Boom. Yeah, if you could just whenever you're finished the lab, take all of your code and all of your materials and just throw it in the Dropbox. I'd appreciate it, even if it doesn't ask for it. I think that the labs could use to be reworked in this class. I also think these lecture slides could use to be reworked. I think a lot of aspects of this course could use to be reworked, but unfortunately I don't have time for it this semester because I'm trying to graduate. Anyway, they're like, but that's what you said last semester. That's what you said a year and a semester ago. It's like, yes, I know. Thank you. So, let's talk about the actual lecture material, shall we? So last time we were talking about the manners in which you can configure input using pull-up or pull-down resistors, depending on whether the input pin is being driven by a high voltage or whether it's connected to a low voltage. Can't you just add the vid to this playlist after the stream ends? Yeah, I know. It's like one extra step that I forget to do, you know? Whereas, like, before, last semester when everything was added to the playlist, that's because, like, I had pre-configured the videos to add to the playlist, and, like, whenever I copy the settings for a stream, it copied that setting too, so it was all taken care of, so I actually just have to remember to do it. I have to graduate before my son does. I think if you finished the lab this week, you don't have to go next week. Like, why would you? You know? So let's talk about output. Generally speaking, there are two configurations of output pin that have different electrical characteristics that you should be aware of. Number one is push-pull, right? The other is open drain. We're gonna go through how these work and why you should use one or the other. So with push-pull, right? Internally, you've got two transistors which control the connection to either plus 5 volts or, plus VCC or ground. So depending on how you configure the pin, you can either have a direct connection from 5 volts to the output pin, or you can have a connection directly to ground to the output pin. So essentially, it's like you're driving the output, right? Yeah. The TAs told us that if we finish the demo in the lab period this week, we don't have to go to the next week. Yeah, I agree with that position. So basically, if you've got this thing, if you got a GPIO pin in push-pull mode, if you set the pin 1, it connects that output pin directly to ground via this transistor, PMOS transistor. Conversely, if you drive a 0 to this guy, which is the next diagram, you close the NMOS transistor, which that basically means that the ground is connected, and this guy, like, if it's connected to ground elsewhere, that means if it's an LED, it won't light up. One thing to note, though, very important to note, there are no resistors here, right? So in comparison to the internal connections that we saw with pull-up and pull-down resistors, or pull-up and pull-down configuration modes on input pins. With this guy, there's just a straight shot straight from VCC to the output pin. So, in essence, if you take one of these guys and you connect it directly to ground, you will short out the pin and damage your microcontroller. So while it drives the output, it's also a little bit on the dangerous side. You have to make sure that your circuit is hooked up correctly, or else you could definitely arrive in a position where these guys short circuit. The other thing to be careful about with push-pull gates, if you have any of your pins that are connected together, you can actually short one pin out through another. Imagine you had like pin 1 and pin 2, right? Pin 1, you drive 1. Pin 2, you drive 0. Let's imagine that pin 1 and pin 2 get shorted, accidentally or otherwise, right? They're just connected with no resistor coming in between. The plus 5 volts from pin 1 will travel directly to ground through pin 2, no resistor in between, short circuit, fried board. Or at least you fried those I.O. pins. Where is the 0 and the 1 coming from? So that's coming from the software, right? In a memory-mapped I.O. system, which we're going to get into a lot of detail about memory-mapped I.O. systems, on a memory-mapped I.O. system, basically the CPU has sent either a 0 or a 1 to the output data register inside of the GPIO's mapped memory. That's picked up on by other circuitry and then sent to the GPIO pin. Cool? Sound cool? Hopefully. That's a lot of stuff we're going to cover today. So in essence, push-pull pins can be very convenient because you do not require an exterior connection to plus 5 volts in order for a push-pull pin to work, right? It's like you don't have to set the thing up with ground connected, right? Is there protection from closing both transistors and shorting internally, or are the external shorts the main problem? External shorts are the main problem. Like, if you have 2 pins, they will each have this circuit, right? Like, every single GPIO pin that is configurable in push-pull mode has a separate instance of this circuit going on. So, so you don't have to worry about the thing shorting out internally, but you do have to worry about shorting it out externally by doing something dumb like connecting 2 pins up together with no resistor in between. So that's push-pull. How do we take this information and apply it to our labs or exams? Because there really wasn't much instruction, at least today. It was just digging through code, trying random things, and seeing what they did. So a lot of this information that I'm giving you right now is embedded in the wiring diagrams for the labs, right? So essentially what I'm doing right now is I'm explaining why the wiring diagrams have been configured in the manner they've been configured, right? Yeah. So that's push-pull. The other type is open drain. So, in contrast to the push-pull, open drain has no internal connection to high voltage, or to 5 volts, or I'm just going to call it 5 volts, even if it's not 5 volts. Oh, yeah. Sorry, Ariel. Yeah, so that's actually a good point. So, the question that Ariel was asking is, you know, what if the PMOS and the NMOS transistor are both closed at the same time? But if you look at the way it's wired, the little circle here means invert signal, right? So one signal is inverted and the other is not, right? So they'll never be the same at the same time because one will always, like, it'll be high-low or low-high. It'll never be high-high or low-low because one is inverted and the other is not. So with open drain, there's no internal connection to plus 5 volts. There is just a connection to ground, which may or may not be closed. So in essence, when you drive the pin 0, that closes the NMOS and allows current to flow through the pin, right? So generally speaking, if you're, for example, lighting an LED, it's not necessarily important that the LED be at 5 volts or, 0 volts. What's important is that there's a voltage differential across the component, right? So, so the way that you would be wiring this externally is you'd have your resistor and your LED that were connected to plus 5 volts externally. So the power must come from an external source in this, obviously, because it's certainly not coming from an internal source. But essentially, so when you're driving that pin low, you're opening, or you're draining voltage into ground through the pin. And the current only flows one way into the chip, right? In contrast, when you drive 1, the GPIO pin is floating, or it's in a high impedance state. So, so if you have your LED and resistor, which are connected to plus 5 volts externally, if you drive 1, you'll get the LED not lighting. And if you drive 0, you'll get the LED lighting. So yeah. Any questions about that? Could we use a different voltage source, 12 volts, for example, for the open drain situation? No. That's a very good question, Omar, and I will tell you why. So, the NMOS transistor here will be rated for a certain voltage, right? The NMOS transistor here will be rated for the same voltage that the microcontroller has been rated for. If you apply too much voltage to this guy, or if there's too much amperage going through it, you risk blowing it up, right? And destroying the pin. Generally speaking, do not ever connect more voltage to a microcontroller than it's rated for, even if it looks like it's just a straight direct connection to ground. The important thing to remember about transistors is that it's not like a mechanical switch, right? It's not like you're just closing a metal contact and you can have hypothetically, you can have a large amount of voltage running through that because it's just a metal, just a piece of metal. These transistors are actually, they have sometimes, depending on the size of them, they can have very strict ratings for the amount of voltage and amperage that they can tolerate. So you don't want to blow out your transistors. So a microcontroller would have a combination of the two types of pins. Well, any GPIO output pin is configurable in a modern microcontroller, like an ARM board. It's configurable as either push-pull or open drain. So you can choose which of the two configurations you would like. That being said, if you're working on very small microcontrollers like your Atmels or your PICs or stuff like that, you might not have a choice as to whether you've got open drain or push-pull. And frankly, the smaller the thing is, I would say the more likely it is to use open drain, because if you, as you can see, this has one transistor, and this one has two. So this is a more complicated circuit. So if you're trying to minimize costs, you would just have this mode available. Make sense? So the one thing that you can do with these guys is that you can, like, with the circuit configured in open drain mode, you can take multiple pins and you can actually wire them directly to each other without a resistor intervening. So like, if you have, like, you can do interesting things with this. Like, you can take the OR of signals. You can take the OR of several pins by doing them in open drain. Couple of questions. Can we get a summary of this? And I'm still confused about how transistors work. All right, so there's only so much I can do to explain transistors, because you should have covered, like, knowing what a transistor does is kind of prerequisite to this class, and I'm sorry to say it, and I'm happy to go over it again briefly, but I can't spend too much time on it. A transistor is a solid-state electronics switch. So you have, actually, I think I've got a diagram of them coming up. Do I? Was it before? Yeah, here it is. So, oh, I have a slide on it. Okay. So, the correct way to think about a transistor, right? You've got two sides of it, which are like the two sides of a switch. You have a gate, which controls the switch, right? A transistor is just a switch that can be controlled with voltage, right? Depends on the type of transistor, but if you apply high voltage, or if you apply high to the gate, that connects source to drain. If you apply low to the gate, that disconnects source from drain and puts it in a high impedance state. So it's like a mechanical switch opening and closing, right? Except it's controlled with voltage, and because it's done in like semiconductors, it can be done very, very, very rapidly, like several million times per second. Or, several billion times per second, actually. So very quick, so a summary of push-pull versus open drain. Push-pull is used when you want the chip to provide power. Open drain is used when you don't want the chip to provide power. With push-pull, you have to worry about short-circuiting the chip. With open drain, you don't. There's a quick explanation. I thought floating meant that the output could be either low or high, since it's neither connected to ground or a voltage source. Not like... So it depends on how the thing has been wired externally, right? But there's no point in doing open drain and have this connected to ground outside. Like, it's got to be connected to high. It's got to be connected to plus 5 volts somewhere. Otherwise, there's no point. It's just a bunch of dead wires, right? So no, floating means high impedance, which basically means the switch is open, which means current can't travel through it. In the case of open drain, since this is probably connected to plus 5 volts somewhere else, that means that the voltage that you would see here along this portion of the circuit would be plus 5 volts, and this would be grounded, right? When you close that switch, current starts flowing, right? Current starts flowing. You'd have a resistor here or something like that, right? And the resistor would provide the voltage differential and control the amperage so that you had plus 5 over here, and essentially the effect of the ground would travel up the wire and to the base of wherever the resistor is. Aren't they called base collector and emitter instead of gate source and drain? The terminology will change depending on who you are talking to. But yeah. So let's talk about speed. Generally speaking, there's a trade-off between the speed with which you can switch a GPIO pin and like there are some trade-offs, right? Because you'd kind of think like, well, obviously you'd want as fast a switch as you possibly could get, right? Turns out no. So the higher the GPIO speed becomes, the greater you increase your electromagnetic interference noise and power consumption. So obviously it requires more power to switch faster because you have to drive it harder. But it also, like, when you have current traveling, like you guys all know magnetism, right? When you have current traveling through a conductor, it induces magnetic current, right? Even if it's magnetic flux. Even if it's a very small amount of flux, if the wire is like sufficiently close and sufficiently susceptible, that the magnetism that's induced by the current going through the conductor can induce current in adjacent conductors. It might not be a lot, but this is what electromagnetic interference noise is due to. It can also be caused by electric field effects, but generally speaking, the one that you have to worry about is magnetic inductance. So basically, the faster you switch, the more current you have to drive, the more current, the more magnetism, the more magnetism, the more magnetic interference. So basically, save the high frequency stuff for applications that need it, and if it's just toggling an LED on and off, like low speed, it will still be far, far, far faster than a human being would be able to pick up, right? So you don't need super high speed. However, if you're trying to do something like serial communication, that's something where like your output speed actually has an effect on the amount of data that you can transfer, and the amount of data that you can transfer is, it's useful to be able to transfer more data more quickly, right? So you want to drive the pins a bit harder. Does that make sense? So related to that is slew rate, right? So essentially, software people kind of have this idea that the universe exists in discrete chunks. Kind of like a Minecraft game, Like, there's either a block there or there isn't. The problem with physical systems is that they take time to move from one state to another. Electrons are physical entities, and so are subject to the laws of physics, including physics of, momentum and, that kind of stuff, physical effects. So the slew rate is the voltage differential divided by the amount of time that it takes to get from your current state to the desired output, right? So what we're essentially talking about when we're talking about increasing or decreasing output speed is we're talking about or increasing or decreasing slew rate. So the trick is, right, in order for this to work as an electronic circuit, right, you have to be in the high state long enough for whatever's reading this to be able to read it effectively as high, right? If you're toggling between high and low faster than the slew rate can get you to the position, you're not actually going, like, you're not going to get anything that looks like a square wave. You'll get something that looks like a really jagged, like, tiny little, triangle wave or something like that. Or if you're doing it, you might get a sinusoid out of that as well. So yeah, slew rate. Let's talk about Schmitt triggers. Again, when you're dealing with actual electricity, the electricity that you are receiving is not necessarily going to be clean looking, right? It's not going to, like, the ideal output and the ideal input are square waves, right? What you actually get is, like, whether it be from the slew rate issues, whether it be through the, the inductance of or capacitance of the circuit itself, whether it be from magnetic interference, that can be either magnetic interference from the mutual magnetic interference inside of the chip or the circuit itself, or magnetic interference from the external environment. Maybe you've got your microcontroller right next to a microwave that's going, or maybe you've got it outside so it's getting constantly bombarded by gamma rays and cosmic rays, or who the heck knows, right? Noise happens, and we have to learn how to deal with it. So the Schmitt trigger is a way of cleaning a signal up so that it can be read more easily. So the problem here, let's imagine that this is a waveform that's received by a microcontroller, and yes, I know there are portions of this diagram that that underhang, which is not something that you would get in a physical system, because that would mean that, like, the voltage would travel forward in time, then back a little bit in time, and then forward again, which doesn't make any gosh darn sense, but, we'll just work with it the way it is. So basically, if you're just watching for whether the voltage is above or below a certain threshold, you might have oscillations around that threshold that don't necessarily mean that the voltage should be considered high. So, for example, these two peaks down here, like, on average, the voltage signal is below the threshold. And despite the fact that it dips down below the threshold here, you might consider the entirety of this to be a high region, right? We teach you how to do circuits with both electrons and tachyons in this class. If you don't know what a tachyon is, look it up after class. They're really cool. It's a particle that travels faster than time, so it hits its target before it's been launched from its source. So I don't think they've been confirmed to exist, but it's like a theoretical result in physics. Anyway, so if you were to just do this according to the trigger, just according to a threshold, you'd get a signal that looked like this, right? You've got low, then you got high, and you can see that all of these little bumps and bruises around the threshold get picked up. What you want to do is you want to emulate a process called hysteresis. Hysteresis. It's it's hysteresis. That's the word. So, essentially, rather than just have a simple threshold beyond which you detect the, you just detect if it's above or below, what you do is you specify an immunity band, right, or a dead zone. Another way of talking about this is calling it a dead zone. So essentially, you separate the threshold at which the signal is considered high from the threshold at which the the signal is considered low. So it's high as soon as it pops over the upper threshold, but it's not low again until it crosses the lower threshold, right? So this little guy, which dips in and then back down again, doesn't count, essentially. These guys don't count either. This little dip down doesn't count. So you end up with a signal after putting it through a Schmitt trigger that's much more clean, much more reliable. One of the problems that we have with electronic circuitry is noise can look like rapid signal. Like, you don't want to pick up noise as part of a digital signal, right? Because, well, you just don't want noise in general, right? So yeah, hysteresis. Any questions about that? I think that's actually time. So, yeah. So if there are any questions about this, please put them in the chat now. I'll also open up the floor to any questions about the quiz. Hopefully everybody thought it was reasonable. Actually, I'm going to do a poll about that. Was the quiz reasonable? My goal is that it was reasonable. What's the simple comparator? That's what you do. It's like, simple comparator just means I'm comparing the voltage to a threshold to see if it's above or below, right? You can sort of liken this to a, like a Boolean, right? It's like, if the signal coming in is X, all this threshold does is it says, it's like a Boolean test, X greater than 2.5. Everyone report poll. Cool. What's the difference between uninitialized and initialized global variables, and how does a multiplexer work? So, good questions all. Well, you know what a global variable is. An initialized global variable, like in C code, right? It's like int x is equal to 10 versus int y, which is just floating there. And then you've got int main, etc. So this is an initialized global variable. This is an uninitialized global variable. And they get stored in different memory. So, how does a multiplexer work? I explained that in a previous lecture, but I'll come back to it. One of my questions asked how many values could be stored in 62 bits. How am I supposed to calculate this? 2 to the power of x. Are we tested on lecture material and textbook material, or lecture material only? Lecture material only. There's way too much in the textbook, and it would be unfair of me to test you on stuff that I didn't explicitly talk about in class. Generally, it's like stuff we talked about in class. Ah, Ariel. That's the formula for the maximum number. But the number of different numbers is just the number of bits to the power of 2. Because you include 0. But why should those be different in hardware? Why should what be different in hardware? Oh, the initialized versus uninitialized? I don't know. Ask the people who designed ARM architecture. A lot of this course is going to be me telling you the how without necessarily telling you the why, because it's sort of a very deep well, you know? Like, what are the advantages of separating these two out? Well, it's like, what are the advantages of keeping your data memory separate from your instruction memory? It's like, in theory, if it's got the same access time, what should the difference be? It's like, I don't know, but they separate it. You know? What is the Fez glyph a reference to? If you've ever played the game Fez, there's like a bunch of like hidden, like, in order to play that game properly, you have to kind of you have to learn like a language that's it's a video game language. Here, I'll show you. That was like a joke answer. These are Fez glyphs. For the labs, the datasheets are humongous. Are there any good getting started guides which you know of? Like the lab document itself, perhaps? How the midterms and exams work, similar to the quiz. At the moment, I'm planning for the midterm and the exam to be similar to the quizzes in style. If you have, of course, if it's a test or an exam, the questions need to be a bit harder. When are my office hours? Wednesdays from 3:30 to 4:30. For the question asking what hardware component creates the clock signal, is the response caps sensitive? No, I don't think so. If it is, I'll fix it, and you can have your marks, because it shouldn't be. I guess I assumed, like, nominal. It's either capitalized at the beginning or not, but maybe, I don't know. Can we only demo labs in person during our session, or can we do it virtually? During your session, please. In person, please. It's orders of magnitude more difficult for you to demo it virtually, so please do not attend labs virtually unless you are in a state of self-isolation because of the current ongoing pandemic-related reasons. Would you test us based on the slides, or would you also ask us stuff that can be found in the textbook? The stuff I will test you on is stuff that appeared in lecture. So it's either it was on a slide, or we talked about it. Right? So take notes. Like, for example, we talked about what a multiplexer was, but multiplexers aren't on the slides, but I tested you on them anyways because we talked about it in class. Speaking of which, one of you asked what a multiplexer is and does. So, a multiplexer is like a way of switching between multiple signals using a digital input. Let me just bring up Krita for a moment so I can draw. For the clock component question, is the answer of the clock acceptable, or is it only the system clock? No, the hardware component that generates the system clock signal is an oscillator. We talked about oscillators. Since these are old lectures but new, old slides but new lectures, that makes sense. I really do try to make sense. It's hard sometimes. So, doesn't a crystal oscillator create the signal clock? Yes. Now that I think about it, I should probably update the acceptable solutions to include the term crystal oscillator, because some people may have said crystal oscillator. Update quiz solutions to include crystal osculator. I wrote quartz crystal. Is that not also an acceptable answer? Yeah, no, that's an acceptable answer. So, as with all of my classes, if you got marked down when you shouldn't have, bring it to myself or the TAs and we'll fix it. So, a multiplexer. Oh, geez. Pop. There we go. So, with a multiplexer, generally they're drawn like this. I apologize, but it's a trapezoid with a bunch of leads coming out of it. And a selector signal. So internally, like, how many pins do I have here? 8? Yeah, actually that works. So, essentially, if you, whatever number is driven at the bottom here, oh, geez. Whatever number you put over these pins, it selects one of these and connects it to an output. So if you, and each one of these will correspond, so it'll be like 0, 1, 2, 3, 4. So if you send, you know, 0, 1, 1, in binary, that's 6. So it'll connect up, you know, 0, 1, 2, 3, 4, 5, 6. It'll connect up this one to the output. That's what a multiplexer does. Are the quiz results available? There are a couple of questions that have to be manually graded, so quiz results should be out in a couple of days, because there's really not much to mark, because it's like mostly multiple choice. Coolio? Any further questions? Writing multiple choice questions is kind of interesting because you kind of have to, like, you have to get into the brain of a student and think, if I were a student who didn't have quite a good understanding of this concept, what would I think the answer would be? You know, because you have to put, like, a couple of tricky, close to correct answers in, right? I don't know, I've never written, believe it or not, in all the years I've been teaching, I've never actually put together multiple choice type, like quiz type tests like this. So it's an interesting thing for me. It's like a new technology that's still very old. Anyway, if there are no further questions, take her easy, folks, and see you all tomorrow. Bye-bye.